All right, perfect. Yeah, thanks very much for the invitation, and thanks everyone for coming. Today I'll be talking about the geometry and dynamics of how do we draw tethers from lipid membrane systems. And so to begin, just with a bit of background, this is a schematic of a lipid molecule. It has a polar head group, which likes water, and two fatty acid tails, which are hydrophobic. And so that means that these kinds of bilayer structures are very energetically favorable because um, they shield the fatty interior from the surrounding fluid. And it turns out that this microstructure actually gives these membranes some interesting rheological or constitutive properties in that lipids can flow in plane like a two-dimensional fluid, while the entire membrane bends elastically out of plane like a shell. And in my opinion, nothing shows this better than the following video from Stephen Bloch's group at Stanford. What you're looking at is a neuron, and that circle is an optical tweezer. And as you can see, when the tweezer plucks up a bit of membrane, it forms a tube. And then as the tweezer moves around, you'll see that the lipids dynamically flow and quickly readjust in plane to accommodate these large out-of-plane shape changes. And so this kind of behavior is only possible for a material that's in-plane fluid and out-of-plane elastic. And one of the main sort of objectives is to be able to describe this kind of behavior theoretically. And so this is just a snapshot from that video, but it turns out that tether formation and tether pulling are used in a wide variety of biological systems, and also sometimes as probes to, for example, measure things like the membrane tension and various forces in biological systems. We've also seen examples experimentally where people have been able to sort of induce tether formation from inside biological systems by, for example, having filaments actually grow and push out against the membrane surface. And finally, there was some sort of recent work that actually showed that in these endoplasmic reticulum networks that there's a lot of tube formation and rearrangement. And I also want to highlight that there was some experiments done about 20 years ago now, where on the x-axis is time. So they were basically drawing a tether in the first half of this figure and then letting it retract, and they were measuring the pull force over time. And so this notion of the pull force is something that we're very interested in describing. And so you'll also notice that in all of these examples, there are very large nonlinear shape deformations in these membranes. And so when we want to be able to describe, how do we actually describe these kinds of systems? So the first thing we want to do is actually develop a theory that's able to capture all the complicated morphological changes that have been observed experimentally. And so I'm just going to go through the different equations that we use to describe these systems one by one. So the first is the continuity equation, which is essentially a statement of local mass balance, which says that the surface divergence of the velocity field is zero. And for surfaces, this actually connects the in-plane and out-of-plane behavior. And here we're treating the membrane as essentially area incompressible. And you can see this for yourself at home with just a piece of paper, which is also area incompressible, because if you have some flow that tends to bring in lipids towards the center, then the surface has to deform to accommodate this flow field. Next, we can look at the in-plane equations. And remember, the membrane is fluid-like, and so we expect to see something that resembles fluid mechanics equations. And so rather than talking about pressures like in 3 dimensions, oftentimes we talk about surface tensions on surfaces. So this parameter lambda is the surface tension, and we can actually have gradients of tension. So this operator is the surface gradient operator. And for membranes, this actually drives a viscous in-plane flow of lipids. So here zeta is the 2-dimensional membrane viscosity, v is again the velocity field, and this is the surface Laplacian operator. And just like we do in 3-dimensional fluid mechanics, it's sometimes useful to write this expression as the surface divergence of the total in-plane fluid stresses to be zero, where here I is the surface identity tensor, and d is 1/2 the velocity gradient plus its transpose. So this looks familiar to us from fluid mechanics. And the last thing we want to think about is the out-of-plane equation, which is sometimes called the shape equation, which is going to look a little bit different. And so the first thing that we see, we'll go through it piece by piece, but the first thing that we see is essentially the Young-Laplace equation, where P is some kind of pressure jump or pressure drop across the membrane surface. And if I were to have a soap bubble, for example, then this pressure would be balanced by surface tension forces, where here lambda is the surface tension and capital H is the mean curvature. Now, we learned in the last slide that membranes elastically resist bending, and so it's perhaps unsurprising to see terms that involve this bending modulus, Kb. And it's not actually important that you know what all these terms mean, but just know that capital H is the mean curvature, capital K is the Gaussian curvature, and so these forces arise essentially in response to an energetic penalty to bending. Now, it turns out this isn't the full story, and actually, even though the membrane bends reversibly or elastically in the outer plane direction, we actually see the presence of some additional forces, where here capital B is the curvature tensor, so it essentially captures all the curvatures of the surface. And we also see this coupling, or this contraction, with the in-plane fluid stresses that we saw in the in-plane equations. And so throughout all of these equations, there's this coupling between the local mass bounds, the in-plane lipid flows, as well as the elastic membrane bending. So we want to be able to solve for the membrane shape and how the lipids are flowing and how the surface tension is evolving over time. And just to summarize some of the key points that we found, we talked about how a gradient in surface tension can actually drive a flow of lipids. We also saw how all of the membrane dynamics are highly coupled together, so we need to solve these equations simultaneously. And finally, we learned about how these sort of viscous and tensile forces can arise in the out-of-plane dynamics, and those perhaps can be important in various biological systems. And so now we are tasked with this idea of how do we solve these equations, which are complicated and fairly nonlinear, and we're going to turn to numerical methods to be able to actually solve them. But recall that we were sort of met with this question because remember that the membrane itself has some in-plane-like behavior and some out-of-plane-like behavior. So we need to figure out what kind of numerical method should we actually use? Should we sort of use one that's more fluid-like or more solid-like to actually describe these membrane deformations over time? So the first attempt that we tried is to use what's called a Lagrangian scheme, which is oftentimes used for solid mechanic problems or problems in elasticity. And I'm just going to sort of show you how it works with a simple schematic. So imagine that this is a side view of my membrane. And generally in numerical methods, we want to introduce some kind of discretization of the surface. So here, these white circles are actually the mesh points in the schematic. And let's suppose that at some time, we have the following velocity field. So this is where the lipids want to go. In a Lagrangian scheme, we have almost the simplest possible mesh motion, which is that the mesh is just attached to the material. So wherever the material goes, the mesh is going to go along with it. And so while this works well for solids, it can actually lead to some problems because imagine if I have some sort of complicated in-plane flows, for example, some kind of swirling flow, well, the mesh is going to become highly distorted, and so it doesn't work that well for in-plane fluids. And also, we can notice that if we have some kind of boundary to our simulation system of this membrane, then because the mesh is following the material, I can actually have boundary deformations. And this is actually exactly what we see when we use a Lagrangian simulation method to simulate tether pulling. So now in the center of this domain, we're simply displacing the center of this patch over time, and indeed we're able to form a tether. And so this video is just progressing by sort of continuously deforming or sort of translating that central element. And now the video has paused and we're just kind of rotating around so you can see that this is a tether from all sides. But we notice a couple troubling features. Indeed, we see that the boundary itself is moving inwards as sort of expected because you have to pull in membrane for this sort of tube area in the center. And also you'll notice that this color scheme is colored by the surface tension. And here we see this sort of characteristic banding in the transition zone from the flat patch to the tether. And we actually think this is unphysical and a numerical artifact, as I hope to convince you in a couple of slides. And you'll also notice there's this region here of low surface tension. And we also think this is unphysical because remember that lipids flow from regions of low tension to high tension. So this would suggest that the lipids are essentially being pulled both into the tether and into the surrounding flat patch, which again, in a slide or two, I'll hope to convince you is actually an unphysical result. So we're unconvinced that a Lagrangian simulation is capturing the correct physics of tether pulling. And so one of the problems with the Lagrangian method is that it doesn't work well with this in-plane fluidity of lipid bilayers. And so we were thinking about whether there's a way that we can actually devise a numerical scheme that better respects the membrane behavior. And so we call this kind of scheme Lagrangian Eulerian, and I'll explain it as follows. We once again have a side view of the membrane system, and let's suppose that we once again discretize the mesh. But the idea now is to introduce a mesh velocity, Vm, which is independent from where the lipids are actually flowing and deforming to, which is just denoted by V. And so here, let's suppose that these dark arrows are where the lipids are actually going to want to flow in this hypothetical example. Well, now we're going to project the velocity in the normal direction and only update the mesh in that direction perpendicular to the membrane surface. And so in this way, we thought, oh, well, now we're not going to have this bad response to in-plane fluid flows. And I actually personally thought that this would be able to successfully form a tether. And this is actually incorrect. So this is a simulation of the exact same parameters. I'm again just trying to deform the very center of this patch upwards using this new numerical scheme. And as you can see, it's entirely unsuccessful. I'm not able to develop a tube, and I actually see these huge regions of surface tension variations. And actually in the subsequent time step, this simulation actually crashed. And so just the method completely fails. And in hindsight, we can actually understand why this is happening, because it turns out that this mesh motion that we chose actually is simply unable to ever form a tether. And so it tells us that the sort of initial guess that we had that this would be successful is unsuccessful. And so at this point, I'd just like to summarize where we are. We found that a Lagrangian scheme, which is used in solid mechanics, fails to handle the in-plane fluidity because it can't deal with these shear flows. And we also find that the Lagrangian Eulerian scheme, or this kind of hybrid method where we project the mesh velocity, entirely fails. And so now we're tasked with this question of, can we devise a scheme that actually better respects the membrane behavior and the membrane constitution? And so we indeed were able to come up with a method. So the first idea is actually shared with the concepts from the last slide, where we have a mesh velocity, Vm, that is independent from how the lipids are going to flow. And it's actually the mesh velocity that's going to completely dictate how the mesh is going to move over time. But the new idea is, what if instead of prescribing the mesh velocity, what if we instead treated the mesh as its own independent two-dimensional material? Because if we have a two-dimensional material, now I could choose, for example, what the stresses in the mesh itself are going to look like. So this is a completely sort of fictional exercise. I can choose the mesh to be in-plane elastic. I could choose for it to be viscoelastic. And all I have to do is then satisfy the appropriate force balance equations for the mesh itself. But you might wonder, well, if I'm choosing some arbitrary material properties for the mesh, how do I know that the mesh is actually describing the correct surface, right? Because we know that the membrane itself is going to want to deform over time. And so it turns out that we can enforce that the membrane surface and the mesh are always coinciding with the following constraint, which we sometimes call the kinematic constraint. So here we're essentially saying that the normal velocity of the mesh must always agree with the normal velocity of the membrane. And we enforce this constraint with the Lagrange multiplier, which is also entirely fictitious. It's just something that enforces this constraint. And if you go through and see how this affects our entire numerical method, it actually enters into our mesh dynamics as something that looks like a body force term, right? It looks like a force that's always in the normal direction, which is essentially constraining for this mesh surface and material surface to always overlap. And it turns out that when you use this numerical scheme to simulate tether pulling, it actually is successful. So here we're solving the exact same problem that we saw previously, where we're just displacing at the very center of the patch. And what we see is the formation of a tether. And now eventually the video will pause, rotate around, so you can see for yourself that indeed we have a tether from all angles. And in this simulation, I actually chose for the mesh itself to behave like a compressible fluid in plane, so it can change its area. And also, it also elastically resists bending. And so we can see a couple of things here. One is that because I have dynamical equations for my mesh, I can actually set boundary conditions. So the boundary of this numerical domain has not changed over time. And also, we can compare this to the Lagrangian simulations that we saw previously. So in this schematic, we have the Lagrangian simulations on the left, the so-called ALE, or arbitrary Lagrangian Eulerian simulations, on the right. And remember, this is the exact same physical process. And so what we see on the left is that the Lagrangian simulations have very distorted mesh elements. And we believe that's the reason that we see this unphysical banding and regions of low surface tension. Whereas on the right, we have a much more well-behaved mesh, and we don't see any of these surface tension variations in the region between the tether and the remaining flat patch. So we believe this is a successful simulation of tether pulling. And for the remainder of this talk, I'm only going to discuss simulation results involving this new numerical method that we developed. But let's turn back for a moment and remember that we were initially interested in describing the forces required to pull a tether over time. So these are simulation results. So on the x-axis is the displacement of that tether versus in units of the radius of the tether itself. And on the y-axis is the dimensionless pull force required to pull a tether. And we can actually visualize what's happening in the sort of different regimes of this pull force development. Because at early times, we have small deformations. And so we see these characteristic tent-like structures. And indeed, the force agrees well with the linear prediction, which is shown in this cyan line. But eventually, we arrive at a displacement that's so large that the membrane begins to undergo a transition from a tent-like shape to a tube-like shape. And so indeed, after we go through this transition, so this schematic is right at the maximum pull force. So after this transition, we actually see a tether begin to develop. And once the tether develops, we can just pull and pull and pull. And the force required to pull this tether is roughly constant as I just sort of continue to pull my tether in agreement with observations that prior studies have made as well. And now that we have a pull force measurement, we can ask, well, what are the different things that we can do to affect how this, the pull force required to pull the tether? One thing we can do is change the membrane geometry. So one thing to note is that from analytical theory, previous people have found that the tether radius is essentially given by a balance between the bending modulus and the surface tension. So this ratio gives you a length scale squared. So the square root of this is telling us about how thick we expect the tether to be. And we want to compare this value to the actual size of the patch itself. So that leads to this dimensionless number, which we call the Foppel-von Karman number, which is essentially the length of the patch divided by the radius of the tether squared. And so we can see what actually happens as I change the patch size. So as I decrease the Foppel-von Karman number, which are lighter and lighter lines in the schematic, or essentially shrink the patch relative to the tube radius, we see that the initial slope of the pull force is changing, even though the long time or sort of steady state pull force remains constant. And so it turns out that these kinds of observations were actually seen previously, more than 20 years ago. And one thing that we can do is remember that the linear theory does a good job of predicting this initial slope. So we can actually return and calculate, well, what is the pull force if we were to simply use just the linear approximation? And so we essentially see that there's a prefactor relating what the pull force is to just the linear displacement of the tether. So we've thrown away all nonlinearities. And we see that when you do this, you get something that looks like a collapse of the data, where especially at early times, all the lines are on top of one another. And so we sort of have captured the geometric effects of tether pulling. But we also remember in that, for example, in this video that we showed on the first slide, that there are actually dynamic effects, right? I can pull the tether at different rates. And indeed, one of these experimental works from 20 years ago actually was looking into what happens as I sort of vary the rate of tether pulling. And it turns out that because our numerical method captures all of the in-plane lipid flows and all of the membrane dynamics, we can actually simulate and see what happens as I pull the tether faster and faster. So here in this legend, this SL is a dimensionless number called the Scriven-Love number, which essentially measures how fast am I pulling my tube relative to the characteristic velocity scale of the lipids that's sort of natural to the membrane. And what we see is that as this pull rate gets faster and faster, so as the color of these curves gets lighter and lighter, we actually are seeing two things. One is that the transition from a tent to the tube happens later and later, so at larger and larger displacements. And also the steady state pull force, or the long time pull force required, is larger. And so one way that we can characterize this is to say, let's just plot this steady state pull force as a function of how fast I'm pulling my tether. So in this case, on the x-axis, we have the rate of tether pulling. And on the y-axis, we have the pull force required at long times relative to the equilibrium pull force. And what we see is that indeed at sort of low rates of pulling, our simulation results agree with a linear theory. But as you pull faster and faster, the nonlinear effects of the membrane dynamics come into play, and we see something that indeed is no longer agreeing with the linear theory. And it turns out that we can also begin to understand these kinds of effects physically, because what is happening, oh, and I also wanted to mention before I say that the quasi-static results were actually very nicely explained in this paper from 2002, and we have now essentially been able to understand, well, what are the actual rate effects of tether pulling, in addition to the geometric effects that we talked about on the previous slide. And to understand this physically, well, let's think about it, right? Because as I pull the tether faster and faster, so I'm inducing a larger velocity gradient. That means that the tension needs to be larger in the tether to be able to pull in these lipids upwards. And the larger tension in the tether itself actually leads to this larger pull force that we see. And the nonlinear effects that you can see in this plot actually arise because of that coupling between in-plane lipid flows and out-of-plane shape deformations. So we actually see that the shape of the tether itself is different depending on how fast I'm pulling my tether. And so the last thing I wanted to share with you is a result that we're actually very, very excited by, which is that our numerical method actually allows us, for the first time, to be able to laterally translate the tether, just like we saw in that first video via an optical tweezer. And so this kind of lateral translation is not possible with those Lagrangian or Lagrangian-Eulerian methods that we talked about earlier. And so we're very excited to see now whether we can understand the forces involved in lateral tether translation. And it sort of introduces a new set of questions for us. And with that, I just want to mention that all of these results were put on the archive in December. And in addition, the code has been released as a fully open source Julia package, which you can download for yourself in just a couple of lines, and also look up how to run the code with the documentation provided. And so with that, I'd like to thank you all for your time, and I'm happy to take any questions.
All right, let's thank Amaresh for the wonderful talk. So if you have any question, you can put it in the chat while waiting for people to type their questions. I also do have a couple of questions. So the first one is a clarification question. So in the new numeric scheme, so how in the new model, how are the fluid flow, the lipid flow, um, uh, characterized? So, because I heard like the whole mesh is considered as a new material, and that there are these out of plane sort of elastic modes, and so I guess I didn't catch how the lipid flow uh, is is characterized in the
Sure.
model.
So perhaps the main thing here is that we're both solving for the the mesh dynamics and the like membrane dynamics separately. So in this, we're still solving for the full membrane velocity field at every
Mm.
time, and so we actually are resolving the lipid flows, but they're just kind of stored in two separate variables. So we can kind of evolve the surface separately from solving for the full dynamics, but the membrane equations are themselves solved just like they sort of should be, I guess. Does that answer your question?
Am I understanding correctly that each time step is broken down into two steps? Like you're solving the sort of elastic part first and then solving the fluid
Uh,
flow. Is that
so
a
we're
good understanding?
so we're actually solving them simultaneously, but we do have kind of two sets of dynamics. We're sort of solving for the membrane dynamics and the mesh dynamics at the same time. So we essentially now have double the equations that we have to solve for, but you can still solve them all sort of together and in a way that satisfies the governing equations for the membrane and this new way that we can satisfy the mesh dynamics as well.
Okay, I see. Um, so a related question is that, how is the boundary condition different in this new model compared to the Lagrangian and Eulerian? So are you allowing, for example, lipid flow through the boundaries such
Yes.
that, oh, okay.
Yes, exactly. So that's one thing that we could do here that we couldn't do previously is that we just set that that sort of the normal displacement doesn't change, but we allow for fluids for additional lipids to flow in through the boundary in a way that we couldn't before. So the whole area of the system is changing over time.
I see, I see. Oh, now I see a lot of questions in the chat. So I'll start with the first one. So maybe Mohammed, would you like to just unmute and ask yourself? Okay, I can also read out the question. So Mohammed asks, is the tether formed by applying a point force in the first place?
Yeah, so rather than actually applying a point force, we're applying a displacement. And so we're just sort of actually moving the mesh itself, but then that allows us to actually track what force is required. Because it would be a little bit hard to do it the other way around because the force itself is such a complicated function of displacement. So that's why we prefer to move the membrane and measure the force in response.
Got it. Um, so we have a second question from Howard. Howard, would you like to unmute and ask? Okay, I can also read that one. So the pulling force varies as log of a parameter. How does the axial distance vary when you transition from the plane to the tether?
Yeah, so this is a great question, and I think actually that Powers paper from 2002 answered it, but essentially the transition from the tent to the tether kind of happens when the membrane sort of sees the boundary. And so I think that is like the log that comes in. It's basically the log of the length of the patch divided by the size of the tether is sort of where that transition from tent to tether happens. So it indeed is sort of um, yeah, it's that logarithmic term is the important part of that transition for where it happens.
Okay, so the next question is from Deepak. Deepak, would you like to unmute and ask?
Yeah, thanks. Yeah, thanks for the great talk. I'm just curious how if you displace not just like in terms of the patch area that you displace, how the pulling force scales with that.
Yeah, so the analytical estimates that we're using all come from just displacing a point force. But again, in that 2002 paper, they do consider what happens if you have sort of a slight area in the center, and just in the limiting case, you get the same sort of point force result. But if you were curious about how the pull force actually does vary with area, it would be relatively straightforward to just measure, like displace a central area and just measure the total pull force on that area.